Good morning, everyone. My name is Bui from Korea Institute of Machinery and Materials. Today, I'm very happy to present our study, Life Cycle Assessment of Hydrogen Produced by a Solid Oxide Electrolysis System. In this presentation, I will examine the simple but important questions. Is hydrogen produced by electrolysis always environmentally clean? I will briefly introduce the background, explain the SOEC system and the LCA methodology, present the main results, and finally summarize the key conclusions. Now, let's start with the background. In the face of climate change, reducing the greenhouse gases like the carbon dioxide is very crucial. Consequently, hydrogen has emerged as a promising fuel alternative due to its high energy and density and efficient power conversion and also clean nature. Moreover, hydrogen serves as an energy carrier for the storage system, addressing the imbalances between the supply and demand caused by the rise of the renewable power generation. Today, the global hydrogen production is still dominated by the fossil fuel. Low emission hydrogen remain below 1%. Hydrogen produced by the electrolysis is considered as the most clean hydrogen, and among the electrolysis technologies, the solid oxide electrolysis cell is one of the most attractive methods because of its high efficiency and less catalyst requirement. However, is hydrogen produced from the SOEC really clean, and which factor has the most contribution to the environmental impact in the SOC system? So this study will firstly quantify the environmental impact of 1 kilogram hydrogen produced by the SOC system. Secondly, identify the dominant contributor to environmental impact and propose an effective strategy to reduce this. This figure shows a 20 kilowatt high power SOEC system. The steam mixed with the recirculated hydrogen, preheated, and supplied to the stack. After electrolysis, the outlet is cooled so that water can be removed from the hydrogen. Air is also heated before entering the stack, while the heat from the outlet stream is recovered. The system operates at 715 degrees Celsius and produces 0.5 kg of hydrogen every hour. It uses 21 kilowatt of electricity and the efficiency is more than 81%. About the methodology, life cycle assessment or the LCA quantified the environmental impacts of the product or system throughout its entire life cycle, from the raw materials extraction to disposal. The assessment used a Recipe 2016 endpoint and the EcoInvent 3.6 database. The functional unit is 1 kilogram of hydrogen produced. The cradle to grave boundary includes the material production, system manufacturing, electricity and the steam consumption, stack replacement and the final disposal. About the inventory, input to the system including the electricity, steam, materials, and energy for manufacturing system. Output from the system is the hydrogen. recipe first evaluates 18 midpoint environmental indicators. These are then converted into the three endpoint damage categories, including human health, ecosystems, and resource scarcity. Finally, they are combined into the single environmental score expressed in points. Next is the SCI result. Within the manufacturing phase, the SOEC stack contributes the largest share, approximately 32%. The air and steam supply system contributes about 23%, followed by the heaters at around 19%. Over the entire life cycle, the total environmental score is the 3.35 points per kilogram of the hydrogen. Electricity contributes approximately 81%, while the steam contributes more than 18%. Manufacturing contributes only 0.6%, and the disposal is negligible. So, cleaning the energy supply is more important than the reducing the hardware impact alone. Our recipe's results shows the impact originate but does not directly compare the SOEC with the conventional production. According to the IEA report in 2024, the natural gas reforming without carbon capture emits about 10 to 12 kg of carbon dioxide equivalent per kilogram of the hydrogen. Coal, coal gasification emits around 22 to 26 kilograms. Electrolysis can be much cleaner with renewable or nuclear electricity. However, when powered by the carbon intensive grid electricity, it can be comparable or even worse than the natural gas reforming. So, the main message is that electrolysis is not automatically clean. So, let's back to our study. Because of the electricity dominates the impact entire the SOEC's lifetime, the case study compares electrolysis with different electri- electricity resources. Korean mixed electricity in the base case will be replaced by the PV and nuclear power. This slide shows the overview distribution of the total impact in each case. The electricity are the main contributor in the case of mixed and nuclear electricity. However, the steam is the main player in the PV electricity cases. Low carbon electricity can reduce the climate related impacts, but it's not eliminated all the environmental burdens. For example, PV electricity increase the relative importance of the land use, the ecotoxicity, and also metal depletion. Nuclear electricity has a greater relative contribution from the ionizing radiation. Therefore, the essay helped the identify the environmental impact trade-off beyond the carbon emission alone. The last, the last graph compare all the cases in the single score. Switching from the mixed grid electricity to the PV electricity can reduce the total environmental impact from 3.35 to 1.14 points, about 66%. In recipes single score results, nuclear electricity gives the lowest total score, only on 0.13, but with a higher ionizing radiation related contribution. Lastly, I will summarize the conclusion. First, the electrolysis is not a miracle machine that automatically produces clean hydrogen. It simply converts the electricity into the hydrogen. Second, the environmental impact of the SOEC hydrogen is therefore governed by the carbon intensity of the electricity used. The last, in this study, replacing the mixed grid electricity with the PV and nuclear power reduced the total impact about 66 and 96%, confirming that clean hydrogen come mainly from the clean electricity. Thank you for attendance.